are a great power source. They convert mechanical energy into electrical energy. The energy of motion is then converted into electrical current. A common example of large generators are windmills. Air currents move the windmill, generating electrical power. However, there are many smaller movements happening all of the time. Is it possible to build a small generator so that it can generate power from everyday movements? Could you charge your phone or even toast a bagel while biking to class? If we build a small portable generator, the sky's the limit.
The entire experiment is based on Faraday's law and the electromagnetic force. The magnetic force on a particle is defined by the cross product of the velocity times charge and the magnetic field. The magnitude can be expressed by the charge times the speed times the strength of the magnetic field times the sine of the angle between the velocity and the field. When the wire is not connected to a voltage source, the electrons inside are at rest. If the wire is placed in a constant magnetic field, there will not be any force on the electrons since they have no velocity. However, if the wire is moved sideways, perpendicular to the field, so that the sine is equal to 1, the cross product will give a force moving the particle along the wire. As long as the wire is kept moving, the particles will keep moving along the wire. The particles now have a velocity in the x and y direction. However, the movement in the x direction is much faster than the movement in the y direction, so the change in the force is negligible. This is the basic principle of induced current. When applying this to the generator, we look at the movement of the wire relative to the magnets. As the wire coil moves around the magnets, the magnetic field is not constant. When the wire passes by the north end of the magnet, the current will move in one direction. But when it passes by the south end, it will move in the opposite direction. This is called alternating current. Because the current keeps changing direction, the voltage will not be constant. Whenever the coil is moving from one end to the other, current stops briefly to change directions. However, if the spinning coil is fast enough, the voltage will effectively be constant.
During our trials for this experiment, we originally tried and failed with many different setups. While we encountered many minor problems along the way, such as flimsy box designs and incorrect box sizes, the major problems we had to overcome were finding the correct type of magnet, switching from an uninsulated copper wire to an insulated copper wire, and initial incorrect usage of the voltmeter, considering our alternating current. Our initial model was rather large and flimsy. It utilized ceramic magnets and uninsulated wire, and furthermore, we learned that our voltmeter was initially set to measure for direct current instead of alternating current. Because of these factors, we were unable to get a reading through our first model. However, even after setting the voltmeter correctly, we were still unable to get any reading. This shows that the other materials we used prevented the functionality of the generator. After conducting more research, we built a smaller, sturdier frame that uses 2 series of round magnets, which acted as strong bar magnets. We used insulated wire, and of course, a voltmeter correctly set to measure alternating current. We also made certain to triple the number of wire coils used to increase the voltage while decreasing the required mechanical energy. The second generator was a success. Not only were we able to measure voltage created on the voltmeter, but we were even able to light up a small light bulb.
Yes! There is a God!
I'm a believer.
It even works when there's a little bit of light.
Oh my gosh!
The light bulb would only be lit if we were able to turn the axle at a high enough velocity. However, when at or above this velocity, the light would consistently turn on, off, and back on, refusing to stay consistently lit, no matter how fast we rotated the magnets. While we were able to successfully create a small portable generator that's able to convert mechanical energy to electrical energy, some problems are pretty obvious when you look at the light bulb we were able to light up. For starters, the light produced was incredibly small, and even then, the light kept turning on and off. The brightness of the bulb itself could be increased by attaching it to something like a bike that could give consistently higher amounts of mechanical energy via pedaling, while compared to our group, which could only increase mechanical energy by twisting the nail faster, which is difficult by hand. Furthermore, adding even more coils of wire around the frame would make the conversion of mechanical energy into electrical energy even more efficient, thus increasing the brightness of the bulb. To correct for the way that the light bulb would switch on and off, you would have to use a device called a rectifier, a small device that can convert alternating current into direct current. This direct current would allow the light bulb to glow consistently if initially given enough mechanical energy to glow.
Now that we know it's possible to build a small generator and we have a few ideas of how to improve, let's think about how we would use it in day-to-day life. Anything with wheels is a great candidate for a generator. A generator on a bicycle while riding to class or a grocery cart while shopping would be very popular, especially for charging electronics. The main thing you have to do is attach magnets or a coil to the wheel. A good design for this could be having a coil rotating between two stationary magnets. This could be put in a small box right on the axle of the wheel. The tricky part is making it small enough to fit, but this could be easily taken care of by using smaller wire and small but powerful magnets. We could charge our phones and toast our bagels just by continuing our everyday activities. Isn't physics cool?